Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks for coming here. So it's my great pleasure to introduce Professor Jan Vitak from Purdue University. He's also a chief scientist from Fiji Systems, a VM startup. And so Jan has worked on many interesting things, including like systems, embedded systems, real-time systems, and also programming analysis, program languages. So today he's going to talk about scripts and programs. With that, yeah.
Okay. Thank you for having me here. It's a pleasure to be here. So the title of this talk is referring to this desire many people have had for many years to evolve scripts, which are typically thought of as, hacked together, one-shot computations into more robust programs. And the talk will have three parts. I will be telling you about work that we really would have liked to do, but we didn't. Then work that we kind of half did, but I think is interesting enough to tell you about. And then work that we've done, but we don't know if it's any good, so it'll be good to have feedback. And I should say, this has been done in collaboration with a quite large crowd, and both at Purdue and outside of Purdue, together with IBM, Stockholm University, Texas, Arlington, and so on. Okay, so let's start. So the first part here is, this part is really coming from interaction with Tobias Rikstad, who was a postdoc at Purdue, and he was involved in this program which is called Pluto, and it has a long Swedish name that I list here, and I'm not going to garble for you. And we've been trying to, it's supposed to be open source, by law, but it's been 3 years we've been trying to get the code and we haven't succeeded. So what I'm going to tell you here is, based on second-hand story, both Tobias, who knows the developers, and on slides and talks by the developers. Okay, so what is Pluto? Well, in the beginning of this story, there was a Perl program that was put together to perform a simple data migration task. Okay, and it was also a prototype of a larger system that was going to be built by a big American company. And, like these things happened, the larger system had three interesting attributes. It was late, over budget, and unusable. Okay, so what do? Well, you take the script and you make it the program. Okay, so it became a program that is currently managing the retirement savings of 5.5 million people in a small country, the whole of it. 23 billion euros, and it's been developed by about 30 people over 7 years. Okay, so this is all background. Now, from a computer standpoint, here are statistics that are more interesting for us. Pluto is 320,000 lines of Perl, SQL, Shell, HTML databases, 750 gigabytes of data. Has to run 24/7 because people want to invest and see how their retirement savings are faring. And bugs are directly correlated to potential loss of large numbers of dollars or euros in that case. So putting your software engineering hat on, there is one sane reaction. Okay, there's no way this makes any sense, and the Pluto guys use this slide in their talk, so I feel, I'm not doing them, sort of not bad-mouthing them. But it turns out that the system works and has worked for 7 years. So it's sort of interesting to reflect how could they get something that is, from software engineering side, or looking at this as a software engineer, as unlikely to succeed as a 320,000 line Perl program can be? How do they make it? So a number of factors they were highlighted in their talk and discussions with them. One was they found that Perl was more productive than Java. Every time they did internal contests, they would pit their team of guys working with Perl, a team of guys working with Java. Perl would win. As a side note, in that system, all of the critical parts are done in Perl, and all of the non-critical parts are done in Java. Yeah? They used the program. They had some discipline, so they decided that they would throw away many features of Perl, and it ends up looking more like C code. There's like no floating points, no threading, no OO. So it's a sort of subset. Then they decided to take, or they had the luxury to have a database to back up the results. So what they do is, whenever they detect an error, they just abort the day's run, undo all the changes, revert to the morning state, and then figure out what to do about it. So they're fail fast. Last, and I think interesting for some of you here, they use contracts, right? So Perl is not typed. So they came up with their own notation for contracts in Perl, and which looks like this. Here's a contract in Perl, pre-post condition, all that, checking whether the variables have certain types. And this is weaved in the Perl program, and it's actually tested. If the contract fails, you abort, undo. Okay. So looking back at their experience, here's what the developers decided were lessons out of this project. Perl syntax is ugly. They would really like the better language. But again, it was productive, right? They didn't like the fact that it was weakly typed. They would like some more checks. And they didn't like the speed. One of the issues was they have to run the computation once a day. And over the years, the computation time sort of slowly is creeping up on the available 24 hours. So Perl doesn't parallelize particularly well, and they definitely didn't want to try that. And they complained, encapsulation, modularity were not well supported. Okay, so this raises some questions as researchers from the research angle. And the questions we took away from this experiment was, is it possible? So we believe that there are many scripts that start as a one-shot exercise and then stay around for a long time. So is it possible to have scripts and programs? I'm not going to define neither of those terms, but we all have some idea what we mean by that, cohabit in the same language. And can we evolve a script into a program? What does that mean? Well, add the level of assurance and safety that we would like to have to feel safer that this is actually going to save our pension forever, and also maybe get some speed because this will help the compiler to generate more efficient code. Another interesting question that this thing raises is if it's true that Perl plus contract is more productive than Java plus static types, then the question is, are type systems useful at all? Or what are the assertion about, static assertion we want to make about about the dynamic behavior of program that will actually help us be more productive? That's a good question. I don't know. So, these were some questions, and there are some links here to the talks and slides about this. So this got us, started on our project, and sort of the second step. So we started thinking about scripting languages and evolving scripts into program, and we quickly realized that we had very little clue about what a scripting language is. Well, you can take a book, of course, you can learn. But more importantly, what do people do with scripting languages? What do actual scripts look like? So the second part of this talk is going to try to explore. I mean, we have all heard that, if you program in Perl, programmers can do anything, or if you take JavaScript, they can redefine anything. But do they? What is actually the behavior of real-world programs in these languages? So, we decided to investigate this, and we set out two questions. So, assuming that you want to invent a new language or extend an existing language, how much dynamism do you actually need? How many dynamic features do you need to do, most of the tasks that people do with scripting languages? One of the possibilities is, maybe that people use the dynamic features just because they don't know better, because they're, programmers, not real programmers like us. So, we don't know. We have no clue. Another question which we set out to try to answer is, if you had a dynamic language that is out there that has legacy code, can I add a type system on top of it, and get some benefits, get more assurance, get faster runtimes? And here the proviso is without rewriting all the legacy programs and libraries, right? I mean, if you have to change existing code, it's useless, right? You may as well start with a new language. Yeah?
When they reported that they felt more productive in
Right.
Perl, or maybe
Yes.
that was based on measurements, I don't know. Did they give any more details? Because the second slide about they wanted more type
Right.
safety and
Suggests-
better performance sounds like they want Java. So
Right. So no, I don't have more information. I mean, what we wanted to do was get their whole code history and analyze what kind of errors they made over the years, but yeah, that never happened, unfortunately. So I don't know. Yes.
I guess correlated with that, if they were doing these little one-off contests, were they doing maintenance of code or start from scratch?
They were. So my understanding is there were small, little project. One feature, one little thing. So clearly, this is not meant as an indictment of anything, or it's just a data point, and an interesting one because they cared. They wanted to. They are under pressure to go to Java actually internally, and every year they have to face the question, well, will we go? Because turns out they have a hard time finding Perl programmers. But there are many problems. But so anyway, we sort of set out these questions, and we followed what methodology? Well, we decided let's pick one language that would be dynamic, that would be pretty much as dynamic as it gets. So you look in your hat and poof, oh, here's JavaScript. Okay, why JavaScript? Well, it's very dynamic, and it has another very interesting property. You can get running code very easily. And that's really hard with any other languages. If I want to know the dynamic behavior of programs, I have to have programs, I have to have inputs. With JavaScript, just open my browser and poof, click to any link and you have a program and you have its input. So what we did was we instrumented a browser, and we went to most of the popular websites, and they pretty much all have JavaScript on them. We recorded a large number of traces from at runtime, about 7 GB of traces. And then we had an offline analyzer that analyzed the traces for a number of properties of interest. Yes?
Sorry. So I'm curious, when your methodology, you pick JavaScript.
Yeah.
And then you kind of cite, hey, there's all this code sitting in web pages.
Yeah.
And I'm just curious if you thought about, and I'm going to be a little snobbish, that these aren't whole programs architected to run end-to-end. So you might see in Scheme or Lisp or Python.
Yeah.
But you're seeing these little nuggets of one-off code, and perhaps even written by people with no formal training on.
Even better.
Okay.
That is exactly what we would like.
Okay.
We want to see, the bad code out there.
Okay.
So that's, in some sense, that was a plus for us. And then we also had some static analysis that looked at the source code. It's another good thing. You get source code with JavaScript. So in case you doubt, JavaScript is a programming language. And here's a bit of JavaScript code. What does it do? Well, the first thing here is function list is a function that can be used as a constructor, like in C#. And what does it do? It takes this object, adds a field name value and sets its value to v, adds a field name next and set its value to n. Then this bit here says, well, whenever you create an instance of this list, make sure that it has the map method. And the map method is this function that creates does whatever we expect it. But the interesting thing is you can have higher order functions in JavaScript. And here's a little bit of code that creates a linked list, 1, 2, 3. And here's a little bit of code that passes in a closure into the map function. So it's a programming language like we're used to, nothing scary about it, right? Well, yeah, right. So one of the things you have probably observed, there are no type declarations. So no types, all right, that's fine. You can grab any string and eval it. Can load code dynamically. In an object-oriented language, we don't usually do that, but you can add fields to an existing object, to an existing class. You can change methods and add methods and remove methods, so you can do anything you want. You can change the hierarchy. So these are really unfriendly to any kind of static analysis. You can't even get a control flow graph for a JavaScript program without doing a lot of work. And if I throw in eval, you just probably can't. All right, so the corpus we got for our analysis is about 100 JavaScript programs. And in the following slides, I'm just going to give you data on a bunch of them. There's Bing there's Google Mail, Gmail, there's YouTube. Lively kernel is a programming environment written in JavaScript by Sun and other random web pages. Okay? So just to give you a little bit of an idea how big we're talking, this all is. So here is my corpus. So Bing, .NET, all of these guys. Above growing is the size of the source code in bytes. So we're looking at 100K about with, it goes to 400K for Apple Mobile Me, above 500K for Flickr, and Facebook was more than a megabyte. Okay, it just gives you this idea that these are actually big. This is not 5 lines of JavaScript code, and the source and growing down here is the size of our traces, and this gives you a little bit of a feeling how long we interacted with the website. And this line here is at about 5 megabytes. So yeah, I mean this is a little bit harder to understand without knowing the format in which we do our traces. But the point is, some interactions are shorter and some interactions are longer. Okay. So the first thing we wanted to find out, sort of standard metric in looking at programming languages, is what is the instruction mix? How do your program behave? And here's a graph, and roughly, so each bar is a program, a trace, or actually the average over all the traces from one website. And the red part is your stores. The green part roughly corresponds to different kinds of reads. And the topmost blue part is calls. Okay, so this is fairly what one would, probably what one would expect. There are certain websites that are a little bit, right, so these are writes, like I said, reads and calls. Some website, the last one is the average. Some websites are a little bit different, like Image Shack and WordPress that have almost no rights, but yeah, whatever it is they're doing, it's unclear. One observation we made, There is a handful of throws and catch, almost none overall, but it does happen. The other metric, which is of somewhat also standard metric, is how long were the functions that we're executing in number of instructions, and this is giving us for all of the websites the average, and here the average is about 30 instructions long, and there's some variation. Nothing. So one thing that's to observe is they're not that short. I mean, they are actually most of them doing quite a lot of work. This is so we've instrumented the JavaScript interpreter, and we've recorded the number of events in the trace, and there may be a few events, maybe a local variable move that we may not have recorded. But all of the arithmetic operation call, all of the bytecodes mostly are recorded in this. So at the bytecode level, this is at the yes. Okay. So the next sort of slightly more interesting metric is what kind of data do these programs manipulate? So here we look at the allocated data types over all traces. You see there's a large chunk of arrays. There are dates, regular expression functions, objects, instances, that means objects, almost no errors, prototypes, a big chunk of prototypes. What are prototypes? They're like your classes. Why are there so many? Because every function gets one prototype for free. So there'll be always as many as there are functions. And anonymous objects, these are objects that are just created with curly braces without going through a constructor. Breaking this down into websites, we get these cool pictures. What should we get out of it? Is there weird sites like WordPress where the only thing you're creating are date objects? Same thing for Dig. Lively is mostly doing arrays and so on. So there's some things we can get out of this. So now going sort of more towards trying to answer the questions we set out originally, which was could you provide a type system for this? How dynamic is the program? The next thing we did is measure the prototype chain length. So what is the prototype chain length? Well, it's really the closest thing to inheritance depth in JavaScript. So so what are we showing on this one? We're showing the orange gives you the max, the longest chain in the trace, and the brown part is the average. So what can we get out of this? Well, so if you have a prototype chain of 1 on average, that means you have no inheritance because everybody has a prototype for free whenever you're created. So you see a lot of them use absolutely no inheritance or very little. And in the case of Gmail, it goes up to 12 levels of inheritance. So this is already a reasonable hierarchy with some code reuse, and you better understand where you get the code and so on. Now, I should mention that Gmail is compiled from Java code, right? So there may be, correlation here. And of course, you can change your prototype. x._proto changes your parent class. So, life is fun. Evals. So we would like to believe that these programs don't use eval, because it would make static analysis easier. Facebook uses over 7,000 evals in our traces on average. So that's not so good. And everybody uses some, right? So this is 1,000, right? So, you're in the hundreds pretty much everywhere. So what else would we like to believe? Well, we would like to believe that most of the evals out there are really doing deserialization using the JSON format. So there is a format where you can encode an object as a string, and then you give it to eval, and poof, you get the object out. So we looked at this, and the orange part of the bar are the JSON strings, and yeah, we're doing a lot, but that still leaves quite a few things. You know, you have code like this, x.f equals 3. It makes, you know, it's really weird. This is this we've seen actually in real code. I'm evaling a constant string. I could have written that code. There is no good reason why I should use eval to just slow down the virtual machine. So there is code like that. We're trying, so this is still ongoing. So we're trying to sort of split these brown bars into you know, what we call trivial evals that are really not doing anything interesting, and sort of more dangerous one. And you know, the results are there are going to come. So okay, all right. So the next bit that we found out is in JavaScript you can call a function with a 2-argument function can be called with 1 argument or 4 arguments. All right. If you call it with 1, then the second argument becomes undefined. If you call it with 4, you get an array that you can access. So this little bit of code calls a function with, you know, either too few or too many. So how often does that occur in real program? So this is the percentage of functions that have been called with different number of arguments. So 10 means 10% of the functions defined in the program are called with you know, variadic arguments, and you know, you look, the average is way above 10. So, and it goes up to, you know, in Gmaps, over 50% of the functions are called with random numbers of arguments. So, you know, if you expect to get any information out of the signature, you know, you should be careful, right? Not yet. That would be an interesting, yes. And the other thing would be another question which we would like, you know, probably should ask is, are they always called with the same number of arguments or not? And you know, there's fine-tuning here that should happen. But okay.
Like, can you set default values other than undefined?
No, it's undefined. So the next metric, which is really interesting in an object-oriented setting, is you know, the degree of dynamism in the dispatch. So if I call a function, if I have a call x.f, how many, you know, methods do I actually invoke at runtime from this point in the source code? And the larger this number, the more dynamic the program. So we did measure this, and the way to read this graph is this point means the point here means there's about 100,000 call sites that are monomorphic. So from this call site, I always call the same method. So this is very nice. You know, we can, you know, if we knew which one these were, we could inline them, you could optimize, you know, life is good. And there is one here where, let's see, one call site that dispatches to 100,000 functions. And now you start to scratch your head. You say, there are not even 100 function in the source, 1,000 function in the source code. So how could you dispatch to that many, right? So, so we sort of thought, well, what if this was really dispatching to, you know, the same function, but our analysis thought they were different? How would that occur? Well, if I wrote code like this, I have a class or a constructor list, which within the body sets the C field to some function. All right? So what is this doing? Every time I call this constructor, it's constructing a new function object, which has the same body, but you know, is a different function. So in our, you know, sort of first cut of the analysis, we said, well, if it's a different function, we'll record that as a different function. But it turns out that this graph shows how many times do you have, so there's 100,000 bodies that are unique, and then there are few bodies here. There is one body that is shared by 50,000 functions. So that means, you know, there's one thing that has been instantiated 50,000 times. So now if we get rid of this and we go back to the dynamic dispatch figure, things shift quite a lot. So you end up around, I think the number here is 2,000. So the most dynamic call site in our traces dispatches to 2,000 functions that are different. But 2,000 is still a big number, right? So another thing that we found surprising and funny is, so when you think of adding types to a language like JavaScript, you say, okay, how am I going to define a type? What's my notion for a type? Well, one sort of naive way would say, oh, I saw this constructor called list. Well, we'll call that a type. Now, it turns out that constructor is just a function. Say that I took a slightly different definition of a type. I say a type is the set of method and field names. Okay? And now say I look at all the uses of the constructor and look, do I always get the same types, same sets of methods and field names out of it? And the answer is no. So there's about 2,000 constructors that are monomorphic, as in whenever you call list, you get a list out. And then there is one constructor that returns 300 different types. So 300 different sets of field names and method names coming out of this guy. How can this happen? Well, here's an example of code. We say the person, and depending on the sex, we add a field. You know, that would be my son. You know, he likes guns. So that's not too good. So I don't have a slide for this, but we sort of started drilling down into this, and we figured out that these points here seem to correspond to uses of some libraries which implement, you know, inheritance in JavaScript. So really, this we believe we can get this down to about 50. So if we get rid of the special cases, it's still bad, but it's you know, it's not as horrible as this. Now, the last thing we looked at was now assuming I knew a type, is this going to change? Well, in JavaScript, I can always add or delete fields. So do people do that? Well, so what is this? This is per object the number of addition in orange and deletion in blue of fields, right? So per object, so what this means is in Bing, per object I'm adding 0.95 fields and deleting, you know, a tiny fraction. On average. So average over all the objects. So this is maybe not the best way to represent the data, but what it's telling us is there is a lot of adds and a lot of deletes. And that means it's really hard to imagine a static type system. You can imagine if you had only adds, perhaps, but the deletes really screw you up because it's not monotonic anymore. But we thought this is way too much. This is way too much. Yeah?
Did you analyze the deletes to see if they were perceivable?
Sorry, they were?
So maybe they're deleted, but no code actually tests for the member being there? We couldn't do it with our framework because we only do traces, but yes. Yeah?
So you obviously didn't treat indices that are numeric as fields in this?
Oh yes, we did. Where I'm going to come to...
okay.
Yeah. Hold your horses, you're ahead of me. So the first thing we figured out is, well, what we said is after construction, but the question is, what does construction mean? So we decided to take heuristics to say, well, let's change the way we record things, and we say construction is until the first read of a field of an object. So I say I'm constructing an object until I read a field, and I'm just going to disregard all of the writes that happen until my first read and say, you know, this is, you know, the construction phase. If I had a class-based language, I would have defined a class, and since I don't have a class-based language, but I'm obliged to add fields one at a time, well, you know, so what happens? Well, the sort of the faded numbers are what we had before, and if we take construction into account, the numbers go down quite a lot. So there, but it's still there. So the next thing is say, we figured out is yes, in JavaScript, arrays and hash tables are objects. And some of these adds and deletes just corresponds to adding things in an array, deleting things from a hash table. So maybe we can get those out and get a feeling for how the programs would look if you had proper arrays and proper hash tables as data types. So how do we know that an array, that we have a hash table access? Well, you have something like x square braces name for a string. And if it's an array access, it's x square braces an integer. So if we remove those, then the numbers go down. So now we're going, in many cases, you have, fairly low numbers of adds. But in all cases, it still happens. And in pretty much all cases, we still have deletes. So, we put all of the smarts we could to get down the dynamism. At the end, it looks like, yes, these programs are truly dynamic, and there's not much we can do. So, conclusion to this part is, well, the code is really dynamic. Not all of the features are used by all the application, but there's always somebody who does something weird, and so it's sort of not clear to us that there is much hope in imposing a static type discipline on JavaScript without rewriting considerably the legacy code. And then the question is, well, what's the benefit? Yes.
So it looks like Gmail has the most of the dynamic.
Yeah.
And you say it's generated from static Java.
So that could be that our heuristics are not strong enough. It could be that they're doing something that is perfectly reasonable, but we just don't know what, how to interpret that. So yes, clearly. So there, yes, these are heuristics, but yeah, yeah.
Did you look at people actually changing the prototype chain at runtime or doing other really crazy dynamic things like that?
Yeah, so we have numbers, and I think that we found cases where that happens, but I can't recall how much, but there were some, but not, it wasn't, well, anytime it happens, it's significant because it means, you can't assume it doesn't exist. Yes?
I was curious, you're looking at all these websites.
Yeah.
But in this disciplined Pluto project,
yeah.
Did you analyze that code?
No, we couldn't get the code. That was my that's the starter. This was the part of work we didn't do, which we wish we had. We really wanted to get access to that source code, and there's it may happen. We'll have to if we have to sue. I mean, at least in Sweden, they're supposed to hand it over, but they're making some issues with privacy and so. So background, there's work on adding types and doing type inference for JavaScript, on evaluating the behavior of Python applications, stage info formation flow for JavaScript, try to sort of split the problem in, doing static analysis of the parts they could, and, taint propagation at runtime. There is a lot of good work on static type inference for Ruby, but looking at Ruby, it seems that Ruby is better better behaved than JavaScript, because I don't think that their results would carry over to JavaScript. And some more work, the static analysis for JavaScript and so on. Okay, so now the last part. So what do we do with this? So what do we do with this? So we sort of have this idea that we would like to evolve programs, scripts into programs. We've sort of looked at dynamic languages, and we found that they're really dynamic. So how do we proceed? Well, here's our methodology. We said, well, let's just start with a new language. It's always fun to invent a programming language. Have two benefits, n'est-ce pas? You can correct design mistakes, and you don't have a user base. Both things are good. Not really, but they have their advantages. So we decided to experiment, and experiment sort of by saying, well, if we design the language from scratch, where our goal is to be able to go from these scripts to programs, what would be the design decisions we would take? So this is together with people at IBM. We designed a language called Thorn, and in the context of this talk, what is interesting about Thorn is that it lets you let scripts grow by gradually adding encapsulation and modularization features, which are not available in JavaScript and the like, by addition of concurrency and by addition of types. And I think I'll mention all three, but I'll spend a little bit more time on the types, which is because it's maybe the more novel part of the language. Okay, so yes, it is a programming language, and Thorn, this is a simple Thorn program. It's a class-based language. We're defining a list with two fields, head and tail, and there's a map function that does the apply, and here we are creating a list. So nothing's too fancy. Yes?
Not scripting at all, right? Because you have to have type to begin with.
You have, well, it is not scripting at all. So Python, is Python scripting? So defining scripting. So to define, my personal definition of scripting is lightweight and unobtrusive, probably untyped, So what it is not JavaScript. So it forces you to put some structure. I mean, this was a design decision that we decided that a modicum of structure was actually a good thing. And what was the modicum of structure? It's pretty much what Smalltalk would force you to have. A class is declared and it has attributes. And you're going to tell me what those attributes are before I instantiate an object of this class. Yes?
Are your class statements executable statements, or are they compile time?
So there is an interpreter, so you can execute them in an interpreter, I guess, but they think for what you have in mind, they're more compile time. Yes?
Slightly missed. Do I have to house all my code in a class? Is that what you're saying? Or can I have top-level functions?
Well, you can have top-level functions. You can have statements, sort of trying to, yeah, okay. So I'm just showing this to relate to the example with JavaScript earlier. This is the same bit of code done in Thorn, and it's actually shorter than the JavaScript code. So, well, for whatever that's worth. The other thing is, most of the people that do, non-trivial JavaScript will use something to get the power of classes. So we might as well build them in the language. This is what the version 4 of JavaScript wanted to do, and then it got bogged down in politics, and it didn't happen. So very quickly, the first part of the first set of mechanism we want to provide is modularity. So I really don't want to spend too much time on this. I'll just zip past. This is a Thorn script which really is very easy to read. I mean, it does some queries and some fancy operations. And this is just a script. This is what you would write in Perl, and it's actually not much prettier, I would say. No encapsulation, no modularity. So the first thing you may want to do to this thing is, well, wrap it in a class and create an abstraction that has a name. So you say, all right, well, we can create a class. It has a name. This name is be used and blah, and does stuff. And this is exactly the same program, but I've added a class which does a little bit of, adds a little bit of structure. It's still an untyped language, so we don't have types, and we don't have access control. That's sort of hard to do, or we haven't found a nice way to do access control in an untyped language. So what do I mean by access control? I mean, all the fields are really visible and accessible. We could come up with we considered making some field private, but strongly private, as Smalltalk would do, which is you can only use your own version of the field, not even those from an object of the same class. But in the end, for simplicity, we decided not to go there. So that's the first step. Then the second step, if you want to to package code and distribute it, you need some higher sort of bigger unit than just classes, and you need also to support visibility and some access control. And for that, we bring in modules, and modules give you it's a collection of definitions, and what they give you that is a little bit interesting that you don't have, say, in Java, there is a keyword called on, which does a little bit of control over linking. What it says is, import your own copy of that other module inside of this module, which means that if you can have several versions of a parser. One of the examples that I've encountered in Java is you have a big application that they use 2 different versions of an XML parser in different parts, and the only way to do this in Java is to use class loader tricks. Here you can say, well, import my own version of this, and it's local, and it has, and it's different from all the other versions, and the state is not shared, and it is a little bit nicer. And finally, the last encapsulation mechanism, which is still different from modules. So what modules give you is name control over namespace, and a little bit of control over linking. And finally, the last bit we provide is what we call a component. And what a component is really an isolated unit, isolated in terms of no sharing of references. So when I say my counter component here has this, so components can only talk by message passing, so this is a synchronous method of the component, there will be no sharing between one component instance and another. So you're guaranteed by the language that these are completely isolated little islands of objects. So these are 3 different mechanisms for modularity and encapsulation. And components are also our unit of concurrency. Yes? Sorry?
I was going to ask how a component's different than a class, but then you answered.
Right. So here we're spawning a concurrent component and we're sending messages to it. So that there's more to say about it, about concurrency, obviously. I'll be very, very short. We picked this idea that most of the scripts are written sequentially nowadays. And we didn't want to introduce shared memory, and because then you couldn't really, you have to lose that sequential thinking, which is, for a lot of the audience of scripting languages, which is important because, they're not ready for concurrency, period. So what we said was, well, sure, you can think sequentially, and then you wrap it up as a component, and then you get message passing, and this is essentially some form of an actor model. So components, you can think of them as Erlang processes, actors. They have a mailbox. There's some interesting properties, but it's not particularly different. Yes?
Does this mean in one of these invocations of a method on a component, if deep copy marshalling of object subgroups? So
the question is, do we do deep copying? And it depends. If the components are collocated in the same address space, the data types we have support for what we call pure data types, immutable, and these can be passed by value. And otherwise, yes, you would have to do a deep copy. And definitely, if they're in distributed, on distributed nodes, you will end up doing copying. But I think here the idea is, what is a simple concurrency model you can slap on top of the sequential model without completely breaking down your sequential programs? Yes. Yeah.
So when one component calls another component, waits for it.
Or you have sync and async. So there's a sync call and there's an async call.
It actually blocks the thread, or it gets preempted?
Oh, you're thinking implementation now. That's a choice. It's deep. So let's see. What do those are current? So we have 2. I think we've tried both. both cases. One thread per component, and sometimes thread hijacking. You can play around with what works best. Yeah. So that's about all I want to say on concurrency. And the last bit of the talk is how to add types. To recap, dynamic type checking is great. Anything goes. You can do anything until it stops working. And one of the benefits of dynamic typing is also you can run a program even when bits are missing. You can, and that is good. That's actually good. You can run broken programs as long as you don't need the parts that are broken. Just do that. And static typing, we know and has the good properties that you get earlier warnings and you can generate faster code. So the question was, well, can we have both of these in the same design? So how shall we do this? Well, here's an example. So here's a bit of code in Thorn, say, and there's a class foo that has a method bar, which takes an x. And let's assume that, until now I've shown you completely untyped code. Let's assume that we had a syntax for writing type annotation. :int, let's say, means, x is expected to be an int. And, so for instance, I can create a variable a of type foo, and, all right, so let's say we do that. So what we really want to do is to be able to call typed code from an untyped context, or more specifically, called a.bar with an x, where x is an untyped value. We would like to do that because that lets us interface typed and untyped code. So how can we do this? Well, what we could do, it's easy enough, is you say, well, maybe the runtime can check that x is actually compatible to the type that you declared, But then the question becomes, when do you perform the check? How long does it take you to do this check? If it's really fast and you can do it at the call, then life is good. But it turns out that that's not the case. Well, for int, it's probably going to be the case, yes. But let's take a sort of slightly more interesting example. Sort of same kind of thing. You have an interface ordered that defines just one operation, compare, that takes an ordered and returns an int. And then you have a function sort that takes an array of ordered and returns an array of ordered. And then you have a call to sort with an x where x is unknown. So same question. When do I do the check? How long does it take to do the check? So say I do the check here when I call it. How long does it take me to do the check? Well, I have to check that x is an array. That's probably fast. And then I have to check that all the entries of x are ordered. Best case, linear in the length of the array. Million entries, million operations. Okay? But that's not the worst of it. Let's assume that the array is mutable. Then, right after the check, somebody else could update one of those entries and invalidate what I've just checked. And then, then I can't do anything. Then it becomes nonsense. So, idea that other people have had, this is not one of ours. What if you said, well, we'll add a wrapper around the value, and that wrapper will check that all the interactions between sort and that unknown values obey the contract that this is an array of ordered values. So here we're putting a dynamic contract around the variable, or the object pointed to that variable, and the contract is simply make sure that when you interact with this thing, it behaves like an array of ordered. If at any point of time it stops behaving like an array of ordered, what do? Well, you throw an exception, say. Okay? So, in some sense, what the compiled code would look like here is, when you call sort, you add this little operation here, which is create me a contract or a wrapper around X to make sure that it's an array of ordered. And that's sort of sensible. So you can see that then you can feed dynamically typed value into statically typed code. And if at some point in the computation that dynamically typed value behaves badly, then you will get an error, which is good. The downside of this is you can't really optimize the code. So if you remember our previous example, if this was a static typing context, I could unbox the int and perform the addition on native. I wouldn't have to have objects here. But now, if there's even the possibility that anything that is labeled int is a wrapper around something else, then my compiler can't optimize anything. It has to keep residual code all over the place to check, is this a wrapper? If it is a wrapper, throw an exception. Okay. So that's sort of what was proposed in the past, and we decided to do something different. And this is the design we have in Thorn. And the basic principles we were following is we wanted to be sure that we don't reject correct dynamically typed programs. So the idea was you should be able to add these annotations, and the programs that used to work should still work. And that's there are subtle issues there, because if you're not careful, you can add something that's slightly too constraining, and then suddenly you get a type error, but the program would have worked, and you have to be careful about that. We want to be modular, nothing whole program about our approach. And lastly, we want to make sure that we design something that rewards good behavior. We want to tell the programmer, look, you give information to the system. As a benefit, you will get something out. What can we get out? Well, you can get either a guarantee of correctness or faster running times. Now, the problem with the previous design with the wrappers is there are pathological cases where you can, by adding type information, slow down the program arbitrarily. Because you're creating that at runtime, these wrappers, there's data you're allocating and you have to manipulate. So this is motivation. So what did we do? So we decided to have a type system that is sort of in between static and dynamic. So we call these like types, and the idea is the dynamic parts of the system will be just as dynamic if this was Smalltalk. The static part can be compiled just as if this was C#. And the middle, well, the middle will give you a little bit of error checking, probably not much performance improvement, but a little bit of assurance. That's sort of what we're shooting for. So in our setting, every class named C has a type C and also a type like C. And the compiler will check that if you have declared a variable to be like C, that you actually use it as a C. Example. So here's a class point, which has two fields, X and Y, two methods, and it has a move method, P, which moves the point by grabbing the coordinates of the argument and storing them in the receiver's fields. Here, the fields are declared int, and move, as it stands, is untyped. So here, when we say nothing, think of this, the type is din for dynamic. So what that means is this method will work as long as you feed it something that has getX and getY methods that return ints. Okay? So what we do in our language, if you want to add a little bit of type of safety, is you say, well, maybe I think it should be a point, really. So let's say that I'll write that. I'll write P should be like a point. Okay? So what does that mean? It means that now the body of the method, the scope of P, will be type checked as if P was a point. If I have a type error, this will be caught. So the nice thing with this, well, one of the advantages of this design is flexibility. So we don't prevent code from calling this method with, you know, something completely different. All we're doing is we're type checking the body. So for instance, assume that I had a class coordinate which also has getX and getY, but has nothing in common with point. They're not subclasses, they have nothing in common. They just happen to agree on those two methods. Well, it's perfectly fine. If I have a variable P of type P that is a point, I call move, I can pass a coordinate. The type system will be happy because I've declared P to be untyped, so their type system can't do anything here. And when I call this method, we only said it was like a point, so the type checker, there is no runtime checks. We're just going to feed it through, and it's going to run just fine because C happens to have the two coordinates.
That is essentially then like a shadow interface then that basically replicates. I mean, it's basically like as if you
it's a shadow. It's just like you had an interface for point, and it's just going to check the body of the method, nothing more. Yeah.
I mean, in this case, the coordinate has to have integer declared return types, otherwise it won't work on the method.
Right. Yes. Yes. So it really looks at, you know, we said it's like a point, so we look at point and it says, oh, all right, if I use getX, well, it better have a getX, and, you know, the type is.
Checks more than it's necessary, right? Because maybe you don't depend on that body that the return type is actually int. And so if coordinate were to return something else, it would not type check.
It would not type check. It is. No, you could call it, because we're not doing any type checking at the call point. If C is dynamic, we're saying, oh, whatever, right? So it would fail the type checking here, and then what? Okay, so you
So here's the assumption. So what if you might have more constraints there, say that.
yes, it may be too constraining, but object would be fine. Yes.
So what if the body does not depend on the return type?
Well, then.
And so coordinates say it does not have them as int, right? Then you wouldn't do any optimizations, even though.
No, you're not going to do any optimizations in this code.
So what am I getting?
What are you getting? Well, you're getting this. You're getting. Imagine that now you add one line to your function move, and that line says p.hog. Well, hog is not a method or a field of point. So my IDE now can flag this as a compile time error. Okay? Now, other advantage is I can get name completion, because I've given a hint to my IDE, you know, what is this behaving like? So I'm getting local correctness. It's a very shallow property, but it's useful. You know, especially if you plug this into your IDE. Because you have, you know, now you can have intelligent assist, you can, you know. So that's one thing you get. Compile time errors here. So I'm going long, so I'll skip this slide. So as a summary on this, so a like type is a promise how a value will be treated locally. We still have concrete types. So if you don't say like, you have a real type, and that real type can be compiled efficiently. And when you have something that is concrete, it will never actually, it will never be anything but the type you declared. So the concrete code can be checked normally, and the dynamic code stays dynamic. So like type lets you move slowly from dynamic to static. Yeah.
I have a function with a concrete parameter type.
Yeah.
Can I still call it on anything?
So if I have a function with a concrete parameter type, can I call it, say, with from a dynamic context? Yes, and what you get at that case is a concrete type test. It will say, and it will just reject it if it's not exactly the type you declared. If you have a like type, you can pass anything. Yes.
Still a little confused about, you're saying if you have this like type parameter type, say, then you're saying this method guarantees that it will use it according to that.
It's protocol, yes.
But is that really true? Because suppose I have an upcast, right? That is, I'm passing it into some dynamic context from there on. Then who knows what that context does?
Then who knows what that.
So then that's not true, right?
It is true as long as you're saying this. It's not the okay. So what it really says is this variable will be treated as if it belonged to that type. Now, if you cast this to another variable that has not the object, it's a very syntactic property.
So at the call side, I really have no idea whatsoever what this was.
Yes. Think of it as a type-checked comment. This is what also has been advocated for code contracts. We're moving a comment that the Smalltalk guys would have embedded this in the name of the variable. We're saying just write like this, and the IDE will take care of it, and you get this. All right. So we said we want to reward programmers. So what we did was implement a compiler that uses these like types, and then we took a program and we annotated it and we show the performance of the two versions. So here is the results. Move. So let's see. This is dynamic Thorn. The numbers these are some shootout benchmarks. The numbers are normalized to the performance of Python. So dynamic Thorn is about 1.5 times slower than Python, and sometimes 2 times slower than Python. And with a few type annotations, in the tens, we get to 0.25 or 50% faster than Python. Okay. So what does this say? Well, it says for a naive implementation, this is what you can get. I'm not making any stronger claims than look. With really very little work, we went from something that was slower than Python but faster than Ruby to something that's faster than Python. Yes?
Does the speed up come from adding concrete types or like types?
Good question. Yes. They were mostly for concrete types and mostly because we could unbox some operations on integers. So, take this with as much salt as you want, but it is just, the point I'm making here is, for a very naive implementation of a programming language that, yes, we spent a long time on it, but not much on optimizations. We got big speed up on, 2 programs or 3. So, yes.
By your last comment, would it be if you took like dynamic languages and gave them the option saying like, hey, this has to always be an integer and will always be an integer, and then they could exploit this sort of. You
can imagine that you would get similar speedups, right? So there's a lot of related work. Yes.
So you said you found things were used at different types earlier in the talk.
In JavaScript, yes.
In JavaScript.
Yeah.
Did you break that down at all in terms of ints? Like how often was it that certain objects and other objects were freely mixed, but integers were always integers?
There were. So I really can't answer that one. I don't know. So the question is
programs that are pretty flexible, but if they're indexing into an array, it's always going to be an integer.
So my feeling is that there weren't that many numbers in those programs. It was mostly strings, hash maps, but yeah.
So the annotations that you've added, were those annotations that could have been inferred by a stronger compiler?
Perhaps. I can't say. I mean, we didn't try to infer them. I don't, one would have to look. In some cases, yes. But, the point is, you only have so much time, and, so if you have to spend a lot of time doing your, putting heavy duty, type inference, whole program, control flow, it costs you, yeah. So I think this is, the only point I'm making here is with very little, you can speed up these programs. And that's I don't want to claim more than we've actually achieved. Yes?
So the like types, they help you?
For speed, no.
At all?
not in our current implementation. The ID, the checking, and they're this sort of midway between the two. Meaning the first step of refactoring, you put like everywhere, and then when you sort of are more comfortable, you sort of remove the likes.
So I think you said this, and I just want to make sure. So you weren't doing any inferencing at call sites or through
No.
So essentially what you did is you went into a function, you checked the type, and then for the lifetime of that variable, your calls were optimized.
So you mean these numbers, how did we get them? Or is that the question? Yeah.
Was your basic strategy that you would enter the function,
and
check the type, and then you would just
right.
For the life?
Yes, roughly. Yeah.
So there's another part of this which I'm very curious about, which I'm guessing you haven't done yet, but it's how the programmers will react, because I think they both.
That's the downside of no user base.
But you might. So some of these things like the like types, right? You might catch many more bugs at compile time, so that might save them a lot of time. But they might react allergically to having types at all because they're so used to having dynamic environments.
But then the sort of the selling point is, look, you can get it faster. There's always this sort of hope that give me more information and it'll be faster. Yeah. Well, like types are sort of the gateway drug to speed. You start by putting some like types because they don't prevent you. They don't break your program. As long as it compiles, it will still run.
It's documentation that helps the ID.
Yes.
That's a great thing.
Yeah.
Well, there's some possibility, right, that you could take a program with like types and infer
easily
where those.
So that's what I said. Up to now, we haven't used them for speed, but one could imagine, maybe doing more. Yeah. Sorry?
Same comments.
Okay. So there's a lot of background work. Can't get it all in detail, but it starts with Findler and Felisen on contracts, the Braca work on Strongtalk, the Strongtalk type system, so Smalltalk, gradual typing. There was an effort to do something fairly similar. So ValiScript was never published, but it's a draft that Flanagan wrote for ECMAScript 4, and that had some of the similar features we found out recently, and all of these good things. And this work was done, as I said, in the context of the collaboration with IBM. So concluding, we have a language design that lets us gradually evolve by adding annotations and both concurrency and modularity scripts into programs. We believe that it addresses some of the issues that the people in the beginning of the talk in the Pluto system raised, which were concurrency, modularity, and typing. And one of the things we try to do is make sure that there is a reward for programmers. So you get IDE support, you get potential speedups, so they would use it. And there's a website you can go and play around with the language. Yes.
I'm just curious, because some laugh at me. When you cited the related work.
Yes.
Why did you look at Common Lisp at all?
At Common Lisp?
Which has optional explicit typing.
No. I suspect that it has, either, influenced or been influenced by the works by Felisen, because they have been in the Scheme Lisp community. But yeah, so I haven't looked at Common Lisp itself. Yep.
In a similar vein, how about the runtime type inference work that Chambers and Unger did on self?
So the Scheme community, so Felisen and his students have been looking at soft typing, which is similar to this runtime, for 20 years. And I'll just relate to you his conclusion: it doesn't work. And his conclusion was based on what? He claimed that it's very brittle. Small changes in the program cause changes in your result. You never know. You don't have a performance model. You don't know what the compiler has inferred and what he hasn't. And when you get errors, they're incomprehensible. The mileage may vary and all that. I'm just saying that they've really looked at this, and the Scheme community is at least moving towards declared types in their programs, and they're just giving up on inference. The main problem is that it is not local. And as soon as you go interprocedural, really you tickle it here and it laughs there, and it's just.
Well, the self-work wasn't static, right? It was looking at runtime and looking at at particular call sites, what's the common type of a particular argument, and then I can optimize that path.
So I was thinking about another piece of self-work. There was some work that Palsberg and Agison did. So
this was Chambers and Unger. And
right. Yeah. So yeah, I was thinking about another one.
Has anyone thought about this problem from the point of view of making it purely an IDE issue? So, like, have a strongly typed language and let someone simulate the process of writing in a dynamically typed language and instantly infer the most general strongly typed language that fits what you've written.
So there has been some work on that, and the problem is you get a proliferation of types, and they're not all meaningful, and you have type mismatch. I mean, sometimes the programmer has to change the name of things, or it's just inference doesn't seem to just work very well.
And the speaker then.
Okay.